Hello, everyone. My name is Yubo Liang. I'm the reporter of our BasicTS paper today, and I'm currently a graduate student at the Institute of Computing Technology, Chinese Academy of Sciences. The benchmark described in this article is open source on the website drawn on this slide, github.com, the Shao BasicTS. Firstly, what is BasicTS about? BasicTS is about a multivariate time series prediction. Multivariate time series, aka MTS, contains time series from multiple correlated variables and exists in many real-world systems. Accurate MTS prediction follows a wide range of services related to intelligent transportation, financial investment, and environmental protection. However, despite the significant progress, we find that the evaluation and comparison of existing models are not fair enough, which may lead researchers to make wrong judgments and thus hinder innovation in the field of MTS prediction. And this is the original motivation for the design of BasicTS. Next, I will elaborate on the specific manifestations of unfair comparison in these three dimensions: data level, model level, and evaluation level. We all know that our model needs high quality data to perform well. First, let me introduce unfairnesses from the data level for you. Firstly, the most common source of unfairness is unfairness caused by the lack of richness of the data size. As shown in these two graphs, variables in different kinds of data size tend to show very different trends. Traffic flow data shows good periodicity, while traffic speed data does not show any periodicity. In fact, every data size presents different physical properties. Therefore, if data size that is not rich enough is used in the comparison, it will bring about unfairnesses. Also, at the data level, if different models adopt different pre-processing approaches, the comparison of these their performance results can also be unfair. As shown in the table, applying different data pre-processing approaches to the same model leads to different results. Therefore, it is important to use the same pre-processing method when comparing results. On the model level, unfairnesses can be caused by different pipelines. Pipeline controls many details of the training process. Since each researcher tends to construct their own model pipeline, it may bring an unfair comparison of results. Let's take a look at this table. As you can see, whether or not adding gradient clipping can have a huge impact on the final result. And in the pipeline, there are many details that can affect the results, not only gradient clipping. Therefore, different pipelines can also cause unfairness in the final result. And more importantly, the unfairness is caused by hyperparameter citing. Deep learning contains a large number of hyperparameters, each of which can have a huge impact on the results. In this paper, we show how optimizer and white decay coefficients can affect the final result. Also, we have carefully trained the hyperparameters to ensure the optimal results. Now let's come to the evaluation level. Common evaluation metrics for MTS prediction problems include MAE, MAP, and RMSE. Although they have strict mathematical definitions, the implementation details may vary, such as the way of handling outliers and mini-batch computations. Also, in the field of MTS prediction, the matrix of horizon X is very important. It denotes the error matrix at the number X prediction time step, where many methods make mistakes and calculate the average of the error matrix over 0 to X prediction time step, which results in a significant reduction in error and thus significant unfairnesses. So let me talk about our design thoughts. In order to solve the unfairnesses problem mentioned above and ensure sufficient extensibility, we have the following design ideas. Firstly, we use rich data size. There are more than 10 data size now from different fields. And we adopted a uniform data pre-processing process to address the unfairnesses problem on the data level. Also, we used and for the model level, we used an identical standard extensible pipeline, provided interfaces that allow flexible parameter sightings and we have carefully tuned the parameters of all existing models in BasicTS to address the unfairnesses problem on the model level. Lastly, we used unified evaluation metrics and the pipelines to ensure the fairness on the evaluation level. For the extensibility, we provided researchers with rich, easy to use, and extensible interfaces to configure the standard pipeline and functions. In this slide, I will describe the implementation of BasicTS. The details of implementation of BasicTS is very it's hard to tell. It contains too many things, so I will describe it briefly. The most important of these is unified configuration file. As you can see, we have the various components of BasicTS behind the unified configuration file, which avoids the unfair problem that may be caused by user writing data, user coding, or data preprocessing and other models by himself, and the users only needs to fill in the necessary parameters to run the models, which provides users with enough convenience and fully guarantees fairness. In addition, we also provide interfaces for users to expand the data sets and models by themselves, thus fully guaranteeing our extensibility. Next, I will briefly introduce the data sets and model we introduced in this benchmark. Specifically, we introduced 6 traffic-related data sets, all of which contain a predefined graph, while other data sets such as electricity, ETT, and solar energy and exchange rate, they don't contain a predefined graph. As you can see, they are from different areas. The ETT is electricity transformers consumption, and the electricity is electricity consumption. Solar energy is the power output of some PV plants, and the exchange rate so shows the exchange rate trends of 8 different countries. They don't contain a predefined graph. We think that such data size allows us to measure the ability of our models more comprehensively. In terms of models, we have introduced more than 20 models, including traditional methods and the latest baselines. We believe that such rich models will help to comprehensively compare the performance of each baseline and help researchers to quickly iterate and innovate. We also have some future works. So ultimately, I would like to briefly describe our future iteration direction. In the future, we will introduce data sets from more fields and continue to enrich the methods in BasicTS. We will follow models from recent works. Also, we believe that we will add an assembling module to help users easily obtain better performance. And in addition, we will follow the latest AutoML methods to provide convenience for users to adjust hyperparameters. So this concludes my presentation today. This slide shows our contact information. Feel free to contact us. Thank you for your listening.